I don't know if the let's welcome thing really works when everyone's on mute. But because isn't it a normal invitation for people to clap? Anyway, hello everyone. Thanks, Shadon. It may seem a slightly random topic. This is part of the plan for the next generation Kaldi. As you guys probably know, Kaldi is a speech recognition toolkit that I maintain. But the next generation is going to look very different. Let me explain. Most of you guys probably know this. So Kaldi is in C++ and has some scripts. The next generation is going to be more like PyTorch based or TensorFlow based, but with a bunch of extensions to implement some finite state transducer stuff. So this is the big picture. The next generation Kaldi will basically there'll be PyTorch, but with some extensions to implement finite state acceptors and to make that all differentiable. And then we'll have a separate library called, you can't see on the slide, but Lotse, or Lotse, you guys pronounce it, as a tool for manipulating audio data. Now, so most of this talk is going to be about the K2 portion of the project. That's all about implementing finite state transducers and finite state acceptors in a kind of PyTorch-like way, including on GPU. The goals of this project are that we'd like to implement things like CTC very simply without having to treat it as a special case. Like, you know, there's things like Baidu's Warp CTC, but they're like very specific to CTC. And what I'd like to be able to do is have that as part of a much more general framework where you can also do lots of other things very easily. I'd like to be able to incorporate like decoding graphs so you can constrain the decoding to words in your vocabulary. I'd like to do that, be able to do that easily. And I'd like to do that like all within a familiar framework so that it feels just like programming PyTorch without having to deal with complicated, you know, C++ interface issues. So that's what K2 is about. Now, in this talk, I'm going to focus on a specific problem, finite state accepted determinization. Now, this problem isn't inherently, it's not inherently a super important problem. It's not even necessary for speech recognition, but I'm focusing on it as an example because it's a fairly non-trivial algorithm that we'd like to be able to do in parallel on GPU. And like, if a normal person, if you were to say to a good GPU programmer, implement this algorithm on GPU, they'd be kind of lost because it's really, really hard. So what I want to do is create a bunch of abstractions and tools that will make it possible to do this kind of thing. Okay, so before I explain all of that, I just want to recap finite state acceptors. Here's a little picture, sorry, of one that a finite state acceptor accepts some set of strings. This picture shows one that accepts 0, 0, 1, 0, 1, 1, and so on. I'm not going to go in exhaustive detail here because most of you have encountered this before. But programming-wise, we formulate it as a list of arcs, which would be indexed by state, and then it's a list of arcs leaving that state. And the arc, you can see the whole of my screen, right? Okay, I just can't. An arc is a pair of next state and the symbol on the arc. And to avoid having to deal with any extra information, we constrain that the start state be state 0 and the final state be the last state. And then we add a special final symbol to all sequences, like -1. So that all transitions to the final state must have that symbol. It's just a kind of shorthand so that we can express the final probability on states without introducing extra data structures. So basically, we represent an FSA as a list of lists of pairs, or an arc is a pair. So in practice, we want to deal with weighted FSAs, which is like the previous diagram, except each arc has a cost on it. You've probably seen this formulated in terms of semirings. The normal semirings they talk about, tropical semiring is where you treat the weights as costs. And then if there's two paths with the same symbol on it, you take the minimum cost. The log semiring is where you treat the costs, treat the values like negative log probs. So if there's two paths, you sum the probabilities. You negate, exponentiate, sum, then log, then negate. Conventional tools that deal with FSAs are all templated on the semiring. The approach we're using here is a bit different. The weights are just floats, and they're kept separately from the structure of the FSA. Most of the time, we can avoid dealing with the weights at all in the core parts of the operations. And we're storing the weights with the opposite sign, so it's basically like a log prob. And let's call these scores. And only some operations actually deal with the weights. And these operations they'll come in two flavors. One where it's the tropical semiring, where you take the max if there's two parallel paths. And one where you do the log sum exp, so it's treated like probabilities. It's quite, all of the extended weight types that you can deal with in toolkits like OpenFST are actually implementable easily. There's a slightly different approach where we keep the weights separate, and they can be propagated in the same way everything else is propagated when you do an operation. It's a little bit hard to explain in the abstract, but I'm not going to go into the details of that right now. Anyway, the point is we don't lose we don't lose any generality by doing it like this. Okay. You guys probably know an FSA is deterministic if no state has more than one arc with the same symbol on it. And the problem of determinization is to find an equivalent FSA to the input that is deterministic. So this is just an intro to determinization. As I said, determinization is just an example of a non-trivial problem that we'd like to be able to do in parallel on GPU. So I just want to recap how the conventional determinization algorithm works. Each state in the output corresponds to a subset of states in the input, and the start state of the output is just the initial state of the input, the start state of the input. And the algorithm has a queue of output states that we have to process. And by process, I mean we process the transitions leaving them. Now, it's fairly obvious how we process them. We just look at all the symbols which can leave any of the input states in that set. And then we create the sets of, successor states, and we add an arc. So the algorithm maintains a map from a set of input state IDs to the corresponding output state ID, so that whenever we transition to a set of input state IDs that we've seen before, we make that a transition to an existing state. And otherwise, we like add a new output state, meaning we add a new state in the output FSA. So the weighted version of this, it's like this, but with weights. So we need to come up with a map that maps from the weighted set of input state IDs to an output state ID. And we need to normalize the weights. Normally so that, let's say, the best weight is 0, or the weight sum to 1, or something like that. I'm not going to go into details of that, but the normalization, when we do the normalization, it gives us like the extra part that we normalized away, and that becomes the cost or the weight on the arc that we output. I just want to give you guys some intuition for how the algorithm works. It's not important that you fully understand it. You just have to get the general idea of what's happening. Now, this algorithm doesn't enable very easy differentiation. What we don't want to do, we don't want to have the individual costs be like PyTorch tensors or something and do autogrid on them, because that, first out, that's super slow. Secondly, it gives us a lot of kind of sequential dependencies in the autograd, so that it kind of makes the algorithm, it would make the backprop very slow. We'd like to be able to do the autograd like in one step in parallel. Plus, it would be terrible for round-off, numerical round-off. What we're going for here is to have the algorithm itself differentiable, not like by having autograd inside the algorithm. So as an alternative to the conventional algorithm, we need to use a slightly different algorithm to make it easily differentiable. What we want is we want the output arc weights to be a simple sum of some of the weights on the input arcs. And by sum, I mean like some of the numerical values on the arcs. That way, when we produce the output FSA, we can also produce a list that says for each arc in this output FSA, here's the input arcs that it corresponds to. And then you can easily compute the output weights just in one pass using PyTorch indexing or something. So in our algorithm, the kind of canonical representation of the state subset is a state that we begin from, and then a symbol sequence that we follow. And then the subset of states is just given by that. You follow that symbol sequence, and all the arc sequences that terminate in some state, that's in the subset. So there's kind of two representations of a state subset. There's this like begin state symbol sequence, and then there's the subset itself. And our normalization, instead of like subtracting the best cost, we remove a prefix of the symbol sequence and advance begin state. And we just advance it as far as possible while there's still like a unique prefix, basically before it branches. I'm sorry, I prepared these slides very recently and I haven't had time to make diagrams. So the scores on the output arcs, yeah, I said will be just some of the scores on the inputs. Now, some finite state automata that were determinizable before won't be determinizable with our algorithm. This is actually kind of necessary to ensure differentiability, because if there's ties and you output a structure that merges those, things that have ties on the weights, you don't anymore know how the output varies with respect to the input because the structure kind of collapsed it. So you need to keep things distinct inherently if you want it differentiable. So, like in principle, I just want to explain in principle how you parallelize this algorithm. That instead of processing the queue one element at a time, you process it in batches so that everything that's in the queue you do in parallel. So remember, the algorithm has a queue and you like take one state from the queue at a time. And then of course you put any new successor states on the queue. So now we do this in batches. And the size of the batches will depend on the topology. If the FSA we're determinizing was just linear, this actually wouldn't speed it up. It would be sequential. But in most cases, there's going to be branching. So this parallelization will speed it up. Plus, of course, we're doing parallelization within each state as well. And I'll get to that soon. Plus, we'll parallelize over multiple FSAs in a mini batch, like in real life. I won't discuss that here. I'm going to focus on how we determinize one FSA in parallel. So I want to explain this data structure that's going to be core in the K2 toolkit. It's a list of lists. Now think of this as a generic C++ data structure. Don't think of this as like a sparse matrix or something. That's not what it is. It's an irregular array. So we imagine we append all of the individual lists together. Oh, sorry, wrong direction. We append them all together and then we store the indexes corresponding to the start of each individual list, plus one index that points one past the end of the whole list. So this is the data structure for how we store a list of lists. It's just two linear arrays. And we can also have another level of list by storing a higher level set of indexes. So we could interpret this as a list of lists of lists. Again, like irregular. I just want to explain that the code, I'm going to show you some code in C++. I don't necessarily want to imply that it's just going to have a C++ interface. There'll be a Python interface too, and it would look different. But probably most of these algorithms we'd want to implement in C++ anyway. So let's just imagine it's all done in C++ for now. Okay, so I want to explain some of the basic operations that this toolkit is going to support on lists of lists. So when you want to index one of these things, you can do it in two ways. You can either use the hierarchical index, like where there's two indexes, ij, or you can access the linear list of elements, so list.lms, some other index k. And there's a lot of times when we need to know about the individual indexes of the flattened list. So imagine that for each list object, it has properties index 1 and index 2, or members, say, that contain the individual indexes I and j that you would need to access those elements. So imagine index 1 is a list of lists with this structure, like it has zeros in the first row, ones in the second row, and so on. And list.index 2 is a similar structure that contains 0, 1, 0, 1, 2, and so on. So it contains the second index. And if you want those in flat form, you can get those with .lms. So index 1 and index 2, those are both lists of lists too, but let's suppose they're dynamically created or something. They might not even exist in physical form, but to write algorithms, we'll sometimes need to refer to them. So they might be dynamically created on the GPU or something like that. But for now, just imagine that they're physical lists. Secondly, let list.index be a list of lists containing the flat indexes. So you can see the structure would be 0, 1, 2, 3, 4, 5, and so on. So each list, I've described 4 like extra elements that it has: the LMs, index 1, index 2, and index. And we're going to be needing all of these things in different parts of the algorithm. So I want to start to explain how we'd implement determinalization in this framework. Here's a bunch of declarations. The input of finite state automaton is just a list of lists of arcs. And the output is the same. And I'm not writing how we construct these. The input FSA also has a bunch of costs on the arcs because it's a weighted FSA. So I call these input scores, list of lists of float. The third line, we have a queue of new states to be processed. The fourth line, okay, so this is for each output state, like for each state in the output FSA, it can be represented as a weighted set of input states. So the pair is like an input state and its corresponding weight. And there's another representation, the fifth line, state REPR, state representation, which is what I call this the canonical representation. So it's a list of ints where the first one is the begin state and the remaining ones are the symbol sequence that we follow from that begin state. Next O state is going to be the next output state that we allocate. We have a map. I haven't described how we do the hashing here, but suppose there's a hashing function that goes from the state REPR, like the list in the state representation, to an int64. And we hash that to the output state. So we map that hash to the output state. So now there's a comment there, to do, add initial state. So we do something with most of those variables above to like add the initial state in the output FSA. That's just a set containing state 0 of the input. And then there's a while loop. While the queue is not empty, we process all the elements in the queue at once. And of course, most of the time we'll be adding new elements to the queue, but it's all done in a batch. Okay, so this, let me see. Sorry. Oh, I'm sorry. I can't see the whole of my screen because of the way this Zoom thing works. I was trying to view the whole thing. One second, sorry. Okay, I need to see your screen. Sorry, I can't explain this unless I see the whole thing that you're seeing. Okay, so this subset equals state subsets brackets Q. Well, what this is this is the subsets of input states corresponding to the output states that we're processing transitions from. So the first thing you'll see here is we're indexing a tensor by a tensor. Sorry, when I say tensor here, I'm using that as a shorthand for our lists of lists. So that's one of the fundamental operations that we're going to have to implement. So the next line of code, which is the fourth line, arc indexes equals something. This syntax is actually not how we do this. You see where it says this subset dot LMs dot first. I'm using that dot first to mean we extract the first element of the pair of ints and floats. The syntax would be different than that in reality. Again, this is some kind of indexing operation. We want the flat indexes into the input that we need to access all of the arcs to process. So we're creating a longer list here that contains all of the arcs we need to process. Now, you're probably not following this. In fact, when I read this again, I'm even having a hard time to follow this. The point here, what I want you to remember is just the kinds of operations we need, just to get a flavor of how these algorithms will work. Okay, next line, arcs equals input dot LMs brackets arc indexes. Okay, so we're getting the actual arcs corresponding to those indexes. And this will have the same structure as the line above, as a list of lists. Okay, so next line, O states equals Q brackets, da da da. Okay, so I'm not going to try to figure out what this line was doing. Again, just see that this is a complex indexing operation. We're making use of these .index1 things that I introduced before. Now, it may seem a little bit painful that we have to deal with all of these different types of indexes. You might say, oh, I'd love to be able to just write a loop. Now, of course, if anyone can figure out how to write a loop and then automatically convert that to efficient GPU code that runs in parallel, you know, that would be great. But this is the only way that I can think of to create an algorithm that can actually be implemented on GPU. And then by subset scores. So the actual algorithm, we define this thing called LM that has a bunch of fields, and we define a constructor. And we're basically creating a huge array of these things that conceptually is a list of lists. Of course, in reality, in memory, it's just one big array. So those, after declaring the struct LM, those first 3 lines of code are just like gathering certain information that we need to construct the array. And then the next line, I'm imagining this is some kind of C++ 11 templated constructor where we template it on all of the. Basically, what I'm imagining here is that when we can construct that LMs object, each individual LM inside it gets constructed from the corresponding elements of those arcs of the constructor. And actually, C++ 11 supports these kinds of things. You can have a template with variable arguments, but I'm not. It doesn't even matter whether we do it this way. There'd be a way to do this with append. Like, if you were doing this from Python, there's no such thing as a template in Python because it's not really a typed language in that sense. But you would just do it using append on a bunch of tensors that have the same structure. Oh, of course, you wouldn't be able to call a constructor like that, but basically this LM just contains certain fields of the constructor arguments anyway. So the kind of core of the algorithm, this .sort lists. The idea is LM is a list of lists, and when we call sort lists, we're sorting each of the like sublists. And that kind of, the angle brackets, that's supposed to be some kind of template argument that we supply a suitable comparator that we compare. Let me see the other screen. We compare the symbol and the destination input state, then the negative of the score. What we're trying to do here is we're trying to segregate it so that all of the all of the transitions with a particular symbol are next to each other, because those all go to the next output state. And after we've done that, we partition based on the destination input state and symbol being the same. Let me think about this. Oh yeah, so this next stage, what we're doing is, it's possible that there's multiple paths to the same input state with the same symbol. And if that's the case, we want to take the best one. This is because we're in the tropical semiring. So this kind of indexing expression with colon, comma, 0, that is not really C++ syntax. That's kind of pseudo Python. But what it means is we're taking the first element in each sublist, and that's going to have the best score because of how we sorted. So we're discarding all of the other elements. So, I mean, what I'm trying to get across here is that the idea is we implement these fairly generic algorithms like sorting and indexing in various ways. And those would probably be like templated implementations that we'd have to instantiate. But the point is, things like sorting and these other things, they're generic and they can be implemented on GPU fairly efficiently. Like NVIDIA has this software called CAB that implements things like sorting and like prefix sum, that you can implement these things using those primitives. So the next, the next phase of the algorithm, we have to normalize the representation by removing prefixes of the symbol sequence and advancing begin state. What we're trying to do is we're trying to identify we're trying to identify that if you trace back the best path from any of the current states, you're going to at some point reach a single state, like they'll all trace back to the same state. And we want to identify like when that happens. And then we want to remove any further symbols in the sequence so that we don't go back any further than necessary. Anyway, this can be implemented using kind of primitives that I've already described, sorry. Plus this remove common prefixes. So we suppose that there's like an operation we've implemented that for a list of lists of lists, it'll identify when in the last level, there's some common prefix in the sublists. And then we'll remove the common parts and return that as a list of lists, and then output to this new arc sequences, like the list of lists with the common part removed. So there's a lot of details here that I'm kind of skimming over, and I may actually have skipped a stage or two. And actually, we'd probably have to add another element to these LMs to really do this indexing right. But the point is, you can imagine how we might remove common prefixes isn't such a difficult thing to implement on GPU. The next thing we'd need to do is we need to determine which output states already exist. So this is like the map lookup, but it has to be done in parallel. So we need some kind of map type. And I'm thinking, right now I'm thinking it might end up being a B tree, because that's relatively, it's possible to implement on GPU. A lot of these things have to be decided still, but it's probably going to be some kind of B tree, some kind of hierarchical tree. So yeah, the details here are very much to be figured out. Now, how much time have I used so far? The time is okay? So, okay, so it's the conclusion now. So as you can see, I haven't like dotted all the I's and crossed all the T's, but I'm describing to you the general plan of how I'd like to do next generation CalD using these fairly general purpose toolkit that lets you implement complex things on a GPU. Now, the purpose of this toolkit is so that we can implement ASR decoding and things like that on the GPU naturally. And right now, the difficult part is I'm trying to figure out like what primitives to implement inside this toolkit and like what all the data structures will be. So it's not really, it's a little bit different from what things like PyTorch are doing, because things like PyTorch, it's always regular tensors like rectangular arrays. And we're mostly doing matrix type things like multiplication. What I'm going for here is something a little bit similar, but aimed more towards generic algorithms, mostly on discrete things like integers. Once we do this, there's natural ways that we can do the differentiability part. Like I told you before that each output arc, the weight is just a sum of the input weights. So once we've done the hard part of the algorithm, the actual autograd ends up being pretty easy. So yeah. So maybe that's it. Sorry guys, the slides weren't great. A lot of this is quite new material, so you know, I didn't have time to make pretty pictures. So thanks.